Okay, you have now completed looking at all of the wave phenomenon, and we've actually finished talking probably about reflection and refraction in class. And now I want to talk about interference. And this is an image that you had in the working through the lab. I just want to remind you that you have these two sources sending out the waves, and that the points where the waves are canceling one another out, and also the lines where compose the points where the waves are reinforcing one another, are all lying along hyperbolae, that where the difference between the two stays the same. Here for this red dot, you have gone one wavelength from the yellow source, and you have gone 1, 2, 3 and a half. So the difference between 1 wavelength and 3.5 wavelengths makes this 2.5 wavelengths difference. They are 2.5 wavelengths out of phase, which causes there to be cancellation here. And for all of these other points here, 2.5 wavelengths further from the blue source than the red source, and there's a hyperbola. Here you would have all the points that were 2 waves further from the blue source than the yellow source. Let's test it out. Let's take this one right here, which is 1, 2 from the yellow source, and 1, 2, 3, 4 from the blue source, so they're out of phase by 2 wavelengths. And so you get crest on crest and trough on trough. You get this, here you see the solid lines crest on crest, and here dotted lines trough on trough, antinode. Here they would be 1.5 wavelengths further from the blue than from the yellow. Here they would be 1 wavelength further from the blue than the yellow. Here 0.5 wavelength further from the blue than from the yellow. Here 0 wavelengths further from the blue than from the yellow. And so you get this pattern of hyperbolas. Further in the naming of these, this is called the 0th antinode, and this is the first nodal line. This would be the first antinodal line, the second nodal line, the second antinodal line, the third nodal. So you start in the center along the perpendicular bisector of those two, and then you number them out as you go out from there. And the same thing happens over on this side. Here it is again, talking about how much out of phase they are. As you go further away from the central antinodal, the out of phaseness becomes bigger and bigger. That if you went to the most extreme position out here, then the difference in the distance, like this point here, you are looking at the difference from that source and this source. But if you went to this most extreme difference, then the maximum difference in the distance from the two sources would be the distance between the two sources. That you cannot get a path difference that is bigger than this separation of sources. You can get a path difference that's 0, and you can get a path difference that gradually gets bigger and bigger and bigger as you go further out, but here you've gone the most out, and that is going to be where you have maximum path difference. As you continue around this way, the path difference is going to go smaller and smaller until you reach the perpendicular bisector, where the path difference will be 0. Well, suppose those two sources were more than 3 wavelengths apart. Then we could get a path difference that would go more than 3 wavelengths apart. So we could continue to get greater path difference than we have here. I mean, if these were more than 3.5 wavelengths apart, then I could get 3.5 wavelengths. I would get one more nodal line out here. If they were more than 4 wavelengths apart, I could get one more antinodal out here where it was 4 lambda. Hope that's making sense. Suppose the separation of these two was exactly 2.6 wavelengths. Could I get this antinode? The answer is no. Could I get this antinode? Yes, because that would require 2.5 wavelengths, and the maximum path difference we can get is 2.6. So suppose the wavelength that you're dealing with here was 10 meters, and the sources were 26 meters apart. Then they would be 2.6 wavelengths apart. But then you would have an interference pattern that only went to here. It would not go out to this antinode. Of course, if you made the wavelength longer, and I hope I'm not spoiling some future question, suppose you doubled the wavelength to 20 meters. Then this would be 1.3. Separation would be 1.3 wavelengths. Oh, well, I could get to 1, but I could not get to 1.5 then. And so my whole interference pattern would just be this central antinode, one node, and then one antinode out here. I would just have this part in here. Recall that there was a question that you had in the lab about when you increase the frequency. Well, that would be decreasing the wavelength, because after all, the velocity is determined by the medium. So if you increase the frequency, if you made the motor run faster, then the wavelength would get smaller. And so this distance of 10 meters here would come to represent more wavelengths. And so you would get a pattern which had more lines in it. And I hope that jives with what you remember seeing. When the motor went faster, you had more lines. When the motor went slower, you had fewer. So we try to apply this idea that here is a point, and you need to look and see whether it's on a nodal line or an antinodal line, and which of those it is on. And then you need to figure out, okay, what's the path difference to every point on this line? What's the path difference to every point on this line? So finally, what is the path difference to every point, this point in particular, on this line? But then to also look at those two distances, and what is the difference? That's the path difference. Here the path is 8 centimeters long. Here the path is 5 centimeters long. What is that difference in centimeters? But what is that difference in wavelengths? And thus I can figure out what a wavelength is that is generating this pattern. Here you have an exercise where you have the two sources are 16 meters apart, and they're making waves of wavelength 10 meters. So which one of these 5 would be what the interference pattern would look like? What you need to do is, if the two sources, source, are 16 meters apart, you need to convert that into how many wavelengths apart are these two sources. Boom, boom. And based on that, what is the maximum path difference you can get, which of course is determined by the distance between the sources. But you want it in wavelengths, not meters, before you try to do that. Um, and here's what I spoiled you for. That suppose these two stay at the same separation, and you were to increase the frequency, which would not change the separation, but it would change what that meant in terms of wavelengths, and that would mean that either the pattern would spread or squeeze up. Either the pattern would have fewer nodal lines or the pattern would have more nodal lines if you were to increase the frequency. And I'm sorry I ruined that for you, but do it anyway. Now, in actual fact, here are, if you like, mathematical formulas. Here is a statement, a mathematical statement of what we've already said, that these are the sources, S1 and S2, and I'm interested in the distance from S1 to some point P, and from S2 to some point P, and so I take the difference in those. There's the path difference, and if it is an odd number of half wavelengths, then P is a node. And if M was equal to 1, it would be a node on the first nodal line. And if M was equal to 2, it would be on the second. And if M was equal to 3, you'd be talking about a node on a point on the third nodal line. Or we can talk about antinodes, where instead of it being an odd number of half wavelengths path difference, here we want an integer path difference, including 0 path difference from the two sources, S1 and S2, to this point Q, which is lying on an antinodal line. And you would say, oh, this is the 0th, so this would be the first, and you would put a 1 in for M, and you would use this formula. But physicists don't do this. It's unfortunate. This makes a lot of sense to me. I didn't get it out of a book. I developed it myself, but it makes a lot of sense to me. But that's not the way physicists like to do interference patterns. That usually they're interested in interference patterns for light, and so they are not looking at waves in a ripple tank. Instead, they have two sources of light, probably slits in a screen, and the light is coming through them, and then they have another screen over here, and on that screen they see an interference pattern with holes and bright spots along this thing. That light is a little bit tricky to look down on and see these hyperbolic nodes and antinodes. You can't look down on light as it comes through and see that, but what you have to do is see the light when it hits the screen. So that's the way physicists like to do it, and they have a formula where they're going to take the distance between where the sources are and the screen, and that's capital L, and then the distance off of the center to the point you're interested in, which might be a nodal point or an antinodal point. And here would be the path difference, the S1P and the S2P, that you would take the difference between them. And this little piece right here would be PS1 minus PS2, would be this thing here. But then for this arrangement, this angle theta here from the center, halfway between the two sources, to the point where we have the node, that angle theta is the same as this angle here if this is a right angle. And we're going to say it's close enough. This is definitely a right angle here, and so sine theta would be equal to x over L. Boom, boom. But I also say that sine theta is equal to the difference between PS2 minus PS1, this little thing here, is going to be equal to d times the sine of theta. Yes, okay. So what we have is d times the sine of theta is equal to that path difference, which we've already worked out needs to be an odd number of half wavelengths. I've written it differently here. But that's an odd number of half wavelengths, and then you take that into, so this 2m minus 1, an odd number of wavelengths, nope, half wavelengths. So if we then divided this through by d, we're exactly going with this formula here, but then sine theta I'm going to replace by x over L. And so this is what you find in your textbook, that for the formulas for an interference pattern. And I hope you see you can get from this, which makes kind of intuitive sense to me, to this one here. And maybe instead of going from that to that, you're just going to memorize this. Whatever. Be sure to distinguish between if you're going to an antinode or a node. Okay, so we need to practice using those formulas, and I'm going to suggest that those are kind of hard formulas to memorize, where I think the ones about the path difference are easy to memorize, but this is the way you do the problem. You're going to have problems like this in the book, so that are assigned for homework, so I want you to practice. Here you have these three distances, not all of which, no, all of which you're going to be using in these formulas, and I want to know the wavelength of the waves that are generating this pattern. And then here is another problem. After you've done this one here, if the third antinodal, but this is, of course, this one here was going to the second nodal, so a new problem. The third antinodal is 3 centimeters from the center, boom, this point halfway between the two sources, on a screen. Also the center would be, the screen is going to be up here, and so there's the center. So 3 centimeters over from the screen, we come to the third antinodal. That screen is 20 centimeters away, not 10 like in this picture, and the two sources are 2 centimeters apart, not 3. What is the wavelength? Good problem. Do it. Okay, moving on from interference to diffraction, and we dealt with the fact that applying Huygens principle, we would say that the part of the wave that is going through this barrier is made up of infinitely many points, and that what we're interested in doing is finding a place where the points cancel, and so what we do is divide them into two teams, the blue team and the green team. That doesn't seem right. I'm going to take a chance here. Oh, stretching this a little bit bigger. Come on, you can talk to me. There we go. Oh, and we lose our right angles. Tough. Okay, so we're trying to find the angle at which a nodal line, and note that we don't get nodes along hyperbolas anymore. This time they're going to be along lines, and we are going to, actually we would do it here in the center, but always when we measure an angle, we're going to measure it to the normal. We emphasized that already when we talked about reflection, and in the stuff that we were just dealing with, the angles would be measured from the normal. That theta that we were taking the sine of to get these things here was measured from the normal, and so too for diffraction. We're going to locate the angle at which things occur by measuring the angle from the normal. But if these two are going to a point that's far enough away, they are parallel lines, and this becomes a right angle here, and so this angle here is also, what just happened? Okay, yeah, this angle here is also theta. Oh, what I'm doing. That both of these two are complementary to this angle here, and so they are congruent to one another. And that what we want is that this bit of extra path that this one went, and that's where I messed things up by dragging, but we'll fix it. Okay. That extra distance that this source went compared to this source needs to be a half a wavelength. Pull this down a little. Okay, so that needs to be a half a wavelength, but you can see that the sine of theta is going to be the opposite, which is supposed to be a half a wavelength, divided by the hypotenuse, which is going to be 1/2 of d, and we got this result for the angle at which a node would occur given a gap of size d and a wavelength lambda. And then we went on from that to dividing it into 4 teams, and we saw that now your sine theta is going to be again 1/2 lambda, but that this distance is going to be 1/4 d away, and so you ended up with this result. And then you divided it into 6 teams, and now it's going to be this result, and that in general the result looked like this, where we have added this n, and that n represents which nodal line you are going to. The nodal line that is closest to the center, the nodal line that is the second one out, the nodal line that is the third one out. There's this formula, and again there is a limit to how big n can be. Just like with interference, you are limited by the separation of sources. Here you are limited by the fact that sine theta can never exceed 1. So n lambda can never be bigger than d. It can be at most equal to d, but it can never be bigger than d. And so that's going to limit how big n can be, how many nodal lines you have, just like there was a limit for interference. In comparing the two, when you can see the nodal lines, you have this very clear difference in the fact that you have hyperbolic nodal and antinodal lines for two-source interference, and you have straight nodal lines for diffraction, which could also be spoken of as multi-source interference. But typically, again, physicists are working with light, and they cannot see these patterns from above, and so instead they work with what they can see when they shine it onto a screen. And there what you would see is that all of the antinodals here are the same intensity and the same width, and here you have the central antinodal being the most intense and the widest, with them getting weaker and weaker and narrower as you go out. That when you shine it on a screen, it would look like this. This is what an interference pattern would look like on a screen, and here's what a diffraction pattern would look like on a screen, with the antinodals getting weaker and weaker, and the distance between the nodals getting narrower and narrower. Or if you were to graph it, they would all have the same intensity, the same width, and here they would have varying intensities and varying widths as you went out.